In this video, we're going to write and solve exponential equations of various types. Rentals in a high-rise apartment building get more expensive higher up since the views get better. The rent on floor 0 is $1,620. The rent increases 3.3% per floor. What is the rent on the 20th floor? Since the rent is increasing 3.3% each floor, this will be exponential growth. So here we have a template for an exponential growth equation. We have the final amount and the starting amount, and then we have the growth rate and the time. All right, we're wondering what the rent is on the 20th floor, so we're looking for y. We start at $1,620. The growth rate is 3.3%, which as a decimal is 0.033. And then we're on the 20th floor, so raised to the 20th power. So this is, we can plug this straight into our scientific calculator, and it will tell us the rent on the 20th floor. So 1,620 times 1 plus 0.033 in parentheses, raised to the 20th power. And when we do that, we get $3,101. For tax purposes, a car rental company assumes each car in their fleet depreciates by 10% per year. If the initial value of a car is $39,200, what will the value be when the car is 18 years old? So this problem will show exponential decay because the car is depreciating. So our equation we can use is y equals a times 1 minus the decay rate raised to the power of t, where y is what the value, where y is what we end up with and a is what we start with. All right, we're looking for the future value of the car, and we know right now it's $39,200, and it depreciates 10% per year, so that'll be 1 minus 0.10 raised to the power of 18. And once again, this is a straightforward calculator problem. Just kind of interesting to look at this number here, so let's go ahead and do that before we type it into our calculator. So the number that's being raised to the 18th power is 0.90. And so what that means is that the car keeps 90% of its value each year. So it's losing 10% each year and it's keeping 90%. All right, when we type this into our calculator, we get $5,884. A company promises to release a new smartphone model every month. Each model's battery life will be 5.7% longer than the previous models. If the current model's battery life is 700 minutes, in how many months will the latest model's battery life reach 2,000 minutes? So this will be an exponential growth situation. In this case, we're looking for how many months this is going to take. So we are missing the exponent. All right, let's fill in what we have. So we want to end up with 2,000 minutes. And we're starting with 700 minutes. And the growth rate is 5.7%, so it'll be 1 plus 0.057 raised to the power of t. Right, our variable is in the exponents, so we're going to end up using logarithms here to solve for t. Let's go ahead and start by dividing both sides by 700. So 2000 divided by 700 equals 2.85714. I'm using lots of decimal places because we're not at our answer yet. Let's go ahead and add 1 plus 0.057. Now we'll rewrite this exponential equation with logarithms. So the base is 1.057, so it will also be the base of our logarithm of the number that is not an exponent, and the log equals the exponent. Right, most scientific calculators don't have a button for a base of 1.057, so I'm going to use the change of base formula to solve for t. So I'm going to use log base 10, so it'll be log base 10 of 2.85714 over log base 10 of 1.057. And when it's base 10, we don't write the 10. And now it's time to go to our scientific calculator and calculate that division problem. And we get about 19 months. A rubber bouncy ball is dropped from a height of 117 inches onto a hard flat floor. After each bounce, the ball returns to a height that is 18% less than the previous maximum height. After how many bounces will the maximum ball height be about 43 inches? This will be exponential decay. In this case, the y and the a are both the bounce height, and the t is actually how many bounces. So we're looking once again for the exponent. So we want to end up with a bounce height of 43 inches. We start with a bounce height of 117 inches, and it bounces 18% less each bounce. So 1 minus 0.18. And once again, we are looking for the exponent. So we'll go ahead and divide both sides by 117 and do this subtraction problem here. 43 divided by 117, that's about 0.36752. And 1 minus 0.18, that's 0.82. All right, our variable is an exponent, so we'll go ahead and rewrite this exponential equation using logarithms. The base in the exponential equation is 0.82, so that will be the base in our logarithm. Of the number that is not the exponent. And the log equals the exponent. All right, we'll go ahead and use our change of base formula to calculate t. And it takes about 5 bounces. The savings account balance is compounded annually. Right now, the account has a balance of $1,647. In order for the account to have a balance of about $4,000 in 20 years, what does the annual interest rate need to be? So this time we're looking for the interest rate. And the savings account is growing, so this will be exponential growth. We want to end up with $4,000. We're starting with $1,647, and we're looking for the interest rate that will get us to $4,000 in 20 years. All right, so this time the variable is not in the exponents, but let's go ahead and get this exponential term by itself. We'll divide both sides by 1,647. All right, we have 1 plus r to the 20th power by itself on the right side. So let's go ahead and undo that 20th power by taking the 20th root of both sides. So those exponents and roots are inverses. So we'll go to our scientific calculator to calculate this 20th root here. So using lots of decimal places, the 20th root is 1.04537. And that will equal 1 plus r. So all there's left to do is subtract 1 from both sides. So we get a growth rate of 0.045 or 4.5%. An architect is designing a tapered office tower where the floor space is reduced by a constant percentage per floor. So just to get a little visual on that, so we have this tall building and it's tapered. So the lower floors are larger than the upper floors. The area of the ground floor, floor 0, is 1,320 square meters, and the area of the 10th floor is 711 square meters. At what percentage is the floor space reduced per floor? All right, this will be exponential decay. And we want to end up with 711 square meters after starting with 1,320 square meters. We don't know the decay rate, but we're going to the 10th floor. All right, we'll get this exponential term by itself by dividing both sides by 1,320. And using lots of decimal places, because we're not at the answer yet, we get 0.5386. And that equals 1 minus r to the 10th power. So the exponent, or the variable, is inside these parentheses with the exponent, so it's kind of buried there. So we want to get rid of that exponent, and to do that we will take the 10th root of both sides, because that will cancel out that exponent. The 10th root of 0.5386 will go over to our scientific calculator. And we get 0.939997. Right, notice we have 1 minus r here, so getting r by itself is just slightly more complicated. To get rid of this 1, we'll subtract 1 on both sides. And when we do that, we get about negative 0.06. That will equal negative r. We don't care what negative r equals, we want to know what r is, so let's divide both sides by a negative 1. And we get a decay rate of 0.06 or 6%. I hope these examples about writing and solving exponential growth and decay problems have been helpful. This is Mr. Ela, signing off.